It's my pleasure to introduce Carlos Morales, a professor of physics at the City College of New York. He received his PhD at Universidad Nacional de Cordoba in Argentina. He was a postdoc at UC Berkeley with Alex Pines, and then went on to City College in New York City. Today, he's going to tell us about the interplay of spin and charge and nitrogen vacancy centers, like his title says here. And please, Carlos, it's yours.
All right. Well, first of all, let me thank you and Joanna for the invitation. I'm really very happy to be here today. As you can tell from the title in the presentation, I'm going to be focusing on nitrogen vacancy centers in diamond. And in particular, I'm going to place the emphasis on their charge states, and I'm going to try to establish a connection between the charge and the spin degrees of freedom. So here is a layout of the presentation. After a brief intro on what the systems are and what sort of background observations we need to keep in mind, I'm going to go to the core of the presentation, which I've divided into 3 segments. In the first one, I'm going to demonstrate that one can actually encode the spin state of NVs into the charge states of surrounding ancilla defects. And then I'm going to go on to show that in the presence of externally applied electric fields, one can actually use the NV centers as probes to study the space charge that builds up when applying optical manipulation of these charges. And finally, I'm going to try, if time allows, I'm going to try to combine these observations and push them into the limit of individual NV centers. So before I move on, I have to say that, well, there's a broad effort out there. Even though for obvious reasons, I'm going to have to focus on the work that my own group does, we're continuously inspired by the similar or related work carried on by other groups. And here I've listed those that I'm most familiar with, but of course, there's many more. Now, we actually started working on this topic a couple of years back when it occurred to me that we can actually combine 2 ideas that were known, or 2 observations that were known at that point in time, which were A, the fact that one can actually use laser light to spin pump NV centers quite efficiently. And the second one, that one can actually use this same laser to control the charge state, to alter the charge state of the NV. And so the idea was that perhaps one can combine these features for applications such as injection of spin polarized carriers in diamond. And it turns out that diamond is actually a pretty interesting platform for spintronics applications. For a number of reasons. Now, in conversations that I had at that time with my friend and colleague, Marcus Doherty in Canberra, well, he realized that actually we can take that idea to the next level and start thinking of carriers as sort of flying qubits that, like photons, can eventually be exploited to transport quantum information and, for example, distribute entanglement between defects in a chip. And this cartoon tries to sort of capture that idea. So I'm not going to focus on this today. And I have to make it clear that there's still a long way to go to realize this vision. Nonetheless, I hope that by the end of the presentation, you're going to come to the conclusion that this core vision is very much alive and kicking. Now, I know that this is an eclectic audience, so I'm going to have to say a few words about the main system we're going to be looking at, which in this case is the Nitrogen Vacancy Center, or NV Center, formed by this substitutional nitrogen sitting adjacent to a vacancy in the diamond lattice. And one first thing that we have to keep in mind is that NVs, as pretty much all defects in, or most defects in solid state materials, they can have different charge states, different flavors, as I like to put it. And these flavors can be quite strong in the sense that by adding or subtracting an electron, one can actually change the properties, the physical properties of the NVs quite dramatically. And here is, let's get started, for example, with the separation between the ground state and the excited state, which for the negatively charged NV, which is actually the charge state that is most studied, amounts to about 1.9 EVs, the equivalent of 637 nanometers. But that separation changes in the neutral NV to 2.2 EVs, or 575 nanometers. And so one can actually exploit these differences in different ways to control the charge states of the NV. And here is one possible route. So let's imagine, for example, that we start with a negatively charged NV, and that we apply resonant or near resonant excitation at 637 nanometers. So if the laser is sufficiently strong, it can happen that there's a two-step process going on where the first photon is absorbed and projects the NV center into the excited state. And while there, a second photon arrives and now moves the excited electron into the conduction band. So then we transition to the neutral NV, or NV0. But notice that because the energy separation in here is larger, we cannot excite the NV0 any longer with red light. And so this has to be looked at as a one-directional process that allows us to go from NV minus to NV0, but not the other way around. Of course, we can excite NV0 if, for example, we use green light. And in this case, again, if and this is a strong enough process, laser, we can undergo a two-step process where we first excite the NV0, and then we inject an electron from the valence band into the ground state, say, and we end up with the negatively charged NV. Now, of course, green light can also excite NV minus, and so green excitation allows us to go back and forth between NV minus and NV0. So this is a bidirectional process. Now, in equilibrium, the ratio between negatively charged and neutral NVs emerges from a ratio between the photon absorption cross sections of each charge state. And it turns out that under green excitation, NV minus is actually more favorable. So just for moving forward, we can take a sort of simplified picture of the dynamics and imagine that when we apply green light, we're essentially preparing NV minus. Starting from NV0, we can always prepare NV minus. If we apply red light, starting from NV minus, we can prepare NV0. That's a simplified picture, but I think will be useful to keep in mind. So let's imagine, to get a taste for how this all works, let's imagine the following experiment, where we first use a strong green laser light to scan an area, a large area where we have to imagine lots of NVs. We initialize them into preferentially NV minus, and then we park a red laser beam right at the center of that area. And then we collect the fluorescence that comes about. And here I'm plotting that fluorescence for different red laser intensities. And we see that in all cases, the fluorescence, of course, decays. And this is because we're converting NV minus into NV0, which are not being excited by the red beam. And so we see this decay. Now, one thing that we learned from this plot already is that if the laser intensity is sufficiently weak, we have a sort of plateau, and this allows us to actually read the charge state of the NV in a non-destructive fashion. So, for example, if we take a weak red laser and scan it around the area of excitation, what we see is the emergence of these dark spots that simply shows us the progressive transformation of NV minus onto NV zero in its surroundings. Now, from this image, one can actually already learn that these charge states are pretty long-lived because it takes quite substantial time to reconstruct these images. And we actually exploited the fact that one can store this charge state for long. Here, for example, to store classical information, and then delete it and then rewrite it in some arbitrary fashion, or even in 3 dimensions. Now, the takeaway message from here is that charge states are long-lived, and we can use them to store valuable information. Now, here comes another ingredient that I want you to keep in mind too, which is the fact that the NV minus is a paramagnetic spin 1 defect that has a non-zero crystal field in the ground and first excited states. And so one can here implement what we call a spin to charge conversion protocol, which essentially amounts to the ionization of the NV minus conditional on the spin state of the NV. And this is an idea that was first demonstrated for NV centers by Michel Lukin's group at Harvard. And later on, Lee Bassett's group at UPenn expanded and perfected. Our contribution here was oriented in this particular case to actually demonstrate the non-trivial fact that one can actually use ensembles, large ensembles of defects similar to what I was showing a minute ago, and still adapt the sequence to work under these conditions. And so here is the same fluorescence trace that I was showing before, with or without microwave, and we see a substantial change that of course changes depending on the frequency that we apply. And so by monitoring this change as a function of frequency, we can reconstruct a magnetic resonance spectrum of the NV here in green that agrees reasonably well with the ODMR spectrum obtained by standard means here in yellow. Finally, another ingredient that I wanted to highlight is the question that has to do with where do the charges that we generate during the park go? And so to address that question, we can implement this type of protocols, simple protocols, if you think about it, where we first start in this particular case using a strong red beam to scan the area and prepare all NVs into the neutral charge state. Then we park a red beam at its center, and finally we use a weak red beam to read an image. And what we see here is the appearance of this bright spot that simply corresponds to the transformation of NV zeros into NV minus. Now, something interesting that we see here is what we actually don't see, which is the fact that all NV zeros that are around remain pretty much unaffected, meaning that charges that are being created over here, in particular electrons that are being generated right here, are not modifying the charge states of this NV minus. The fact that there are charges being created is explicitly shown here, where we apply pretty much the same sequence, except that instead of using a red beam to initialize into NV minus, into NV zero, we actually initialize into NV minus with a green scan. And so what we see here is, again, the appearance of this bright spot at the point of illumination. But here we see the formation of this dark halo that corresponds to NV minus transitioning to NV zero due to the capture of a hole. Now that there are, so the interesting message that we can learn from these observations is that NV minus are very efficient at capturing holes, but NV zeros are very inefficient at capturing electrons. And the fact that there are electrons there can be seen if we, instead of looking at NVs, we look at other defects, in particular silicon vacancies, as in this example, which are also in that same sample, in this particular sample. And what we see that in both cases, whether we prepare it with red or with green, we actually initialize the silicon vacancies into a dark state that ultimately becomes bright when we park the red beam, and that comes from the capture of electrons that render it as a SiV minus. So with this information, I think we can now start thinking of combining different ingredients to do what I think are sort of interesting things. One possibility is the following. Let's imagine that we have here a single or just a small group of NV centers in the negatively charged state, and that we apply a spin to charge conversion protocol here. Now, rather than relying on the charge state of these NVs themselves, we can actually send that information to surrounding defects and charge them in a way that is related or correlated with the spin state of the NV. So this is one demonstration of that idea where we first initialize, in this case, we're actually using NVs as the source, and we're using ancilla defects in the form of silicon vacancies, the very same silicon vacancy centers that I was showing a slide ago. And so we first prepare the silicon vacancy centers with green and red scans into a dark state. Then we apply the spin to charge conversion protocol that combines microwave excitation with laser excitation. And what we see is in here this pattern, rather than a ring, we have a sort of disk, but still this is a region that now has become bright because of the capture of an electron. Now, to see the spin, the influence of spin in this pattern, we can actually take differences with or without microwave, as we did in the past. And what we see here is that when the microwave is resonant with the NV resonance frequency, the zero field splitting, then we get a non-trivial difference here that goes away if the frequency is moved off resonance. So we can actually look at these patterns and integrate out of these fluorescence images a signal that is a spin signal ultimately, and that depends on the frequency of excitation and allows us to reconstruct these magnetic resonance spectrum that again agrees reasonably well with the standard optically detected MR spectrum of the NV shown here in yellow. So we call this ancilla-aided integrated detection, and SOS stands for standard optical sensing. Just for you to follow the notation in the following cartoons. This is how the signal, this spin signal, charge encoded spin signal changes depending on the number of iterations, the number of repetitions that we implement. The growth is not linear, as shown in here, is somewhat logarithmic, and that comes from a subtle interplay of the NVs, but also the charge states of all other defects. I unfortunately don't have the time to get in there, but the bottom line is we can actually choose the conditions that make this signal to noise ratio best. And with that, we can, for example, implement time-resolved protocols such as this one, where we essentially change the duration of the microwave pulse, and we can then reconstruct a Rabi signal of the NVs here at the center of these patterns. And this Rabi signal, of course, agrees reasonably well with the SOS or standard Rabi protocol. But once we have the time dependence in there, then we can think of protocols, arbitrary protocols, literally, that essentially combine or integrate spin to charge conversion and charge storage. Here is an example with a HAN echo that is terminated with a spin to charge conversion protocol. And so here is the echo signal that builds up, and we can measure as we vary tau in this HAN echo. And that agrees, again, reasonably well with the SOS signal. Now, of course, there's no reason why we have to stick to silicon vacancies, and we can think of other defects to do the same job. In particular, we can think of NV centers, and this is an implementation that uses NV centers. Here you see that when we implement the same protocol, literally, that we had before, but this time looking at the NV centers that are initially prepared in the negatively charged state, so they are all bright, and we create then these halo, dark halo that I was referring to a minute ago. We look then at changes in this pattern emerging from the presence of resonant or off-resonant microwave, and we see that these changes give us a spin signal of the NV that, as before, we can then exploit to reconstruct, again, well, for demonstration purposes, in this case, the magnetic resonance spectrum of the central NVs that agrees reasonably well with the standard magnetic resonance spectrum, again, here in yellow. Now, during the course of those experiments, we started thinking of ways to separate different types of carriers to somehow gain additional sensitivity. And we engineered structures that look pretty much like this with some surface electrodes. And we essentially work a few microns below the surface and in between the two electrodes. We actually were surprised to learn that the dynamics in here is way less simple as we had originally envisioned. And so it was actually worth the effort to look at what happens. So here we start, let's start with very simple protocol, similar to what we were using early on. We initialize with green, we park a red green, and then we image, in this case, with a weak orange. And we apply, in this case, a variable electric field. And this is what we actually see. So we start with the same dark halo pattern that we've seen a couple times now. But as the voltage increases, we see the formation of these comet-like tail that corresponds to the drift of holes towards the region of, in this case, lower voltages. The field in all these plots is pointing to the right. Now, in the past, and in this case, it wasn't an exception, we've been having reasonable success in using standard master equations describing the capture of electrons and holes and the generation of electrons starting from NV minus, here represented with Q minus, or NV0 here represented with Q0, and so forth. We actually don't have just one equation, we have a set of equations because we have to include other defects that are also in the material, like, for example, P here representing nitrogens that, as a matter of fact, are in normal CVD grown diamond way more abundant than NVs. And we also have to include electrons and holes and the effect of diffusion and drift on those carriers. And when we actually run this type of calculation modeling, well, we start with something that agrees reasonably well with our observations. And again, in the presence of voltage, trends towards things that we've observed. But soon enough, at values of voltage much lower than what we observed experimentally, we obtain this sort of jet-like patterns that do not agree with what we were observing before. Now, we actually had a better success in approaching, not totally reproducing, but approaching our observations when we start including space charge effects. And that is the field created by other defects as they get charged. And this is shown over here. And an intuitive way to picture that comes from the fact that, well, when we send this green light and we separate charges, we charge defects also that create then its own space charge field, and this space charge field influences the evolution that comes next. Now, we had the idea that perhaps we can actually mitigate the effect of the space charge field if instead of applying a continuous optical excitation, we break it into pulses of green light, overall lasting the same, but say short in duration, say on the order of a millisecond or so. The other was several seconds. And what we do is also we implement a fast switch that allows us to turn on and off the voltage the way we actually want. And so what we find when the voltage is actually zero is the exact same pattern as before. And that is reasonable simply because, well, these dark times, remember the long memory that these charges have. So this dark time doesn't influence at all the dynamics. It's as if everything is frozen in between. But what happens as we start increasing the magnetic field, the electric field in this case, is this pattern now evolves not as we had seen before. We see the formation of jet-like regions, but instead of being, say, one directional, we see them bidirectional. And so this is an indication that, yes, well, we can somehow mitigate the jet-like structure shows that somehow we're better mitigating the space charge field. But on the other hand, the space charge fields are acting and actually kicking carriers in the opposite direction of the field while the field is off to form these other jet-like pattern. That we can control with the duration of these other pulses. So one first conclusion that we can draw from this is that these fields can be really quite strong, actually as strong as the fields that we're applying externally, which are already quite strong. So one question was, well, isn't it possible to then somehow craft the charge in the surroundings of the NVs to guide these carriers in particular ways? And so for that, to actually prove the point, we implemented this. This is a simplified protocol where, well, we do the parking, the pulse parking with fields on and off as before. And then we apply a long continuous pulse. And the idea is that, remember, this one should give us jet-like patterns. This one should give us halo-like patterns. What we observe is the formation of this pattern here. Let's focus on the dark region here, which to start forms on one side only, the opposite side of the direction expected for the external electric field that we apply, meaning that there's a strong space charge field acting on these holes. And second, we see it that they somehow follow the blueprint of the jet-like pattern that we created first with these pulses. So the story here is more complex. I will be happy to discuss some more later on, but I simply wanted now to give a flavor for the fact that we can, in principle, imagine guiding these carriers with crafted space charge fields. The possibility that we can do this and monitor essentially the trajectory of these electrons as they drift and diffuse makes us think of different possibilities. And here is one where we started playing a little bit with the magnetic field before it was absent. We turn on a magnetic field in here, this time on the order of 3000 Gauss. And the idea is, of course, to see if we can actually pick up some the effect of a Lorentz force, which by taking differences we see appearing in this pattern here. Now, interestingly, we see these patterns actually form only on one side, meaning that somehow the Lorentz, the velocity of carriers on this side of the pattern is different, probably faster than on this other side. But I won't get into the details, in part because this is ongoing work, and in part because, well, this could actually be the subject of a different talk. Finally, I wanted to highlight the fact that most recently we started working in collaboration with people at Sandia. And we then tried, the goal was to transition to settings where we could actually work with individual or small groups of NVs that we could create at predefined locations. And so the advantage of going with this type of accelerator that only Sandia here provides is the fact that we can go deep about 10 microns or 12 microns, and still make it sort of precise in the way we localize, we create these islands. And here are different examples. I'm going to focus on this one, this type of arrays in here. That here is another example. We actually didn't lower the fluence sufficiently, but we can see that even in some locations, we can start identifying individual defects. And on some more rare occasions, we can actually work with, find situations where we have, say, individual defects that are a couple microns away, in this case, 5 microns. And we can start now thinking of, say, one NV serving as a source, the other NV serving as a target. Now, if we look at G2s, in reality, we see that these are not individual NVs, these are pairs of NVs, but for practical purposes and for simplicity, I'm going to refer to these as individual NVs. So here is, again, the same type of protocol that I was talking about before. We are monitoring in here the target NV as we excite the source NV. And we see that, well, here we cannot see the formation of a halo, but we can see the target NV bleaching as we change the duration of this green park. And we can actually monitor then, extract rates for the bleaching for different intensities and plot that as a function of power. I'm going to return to this graph in a minute. I know that we're running out of time, so I simply wanted to make the point that we can actually, if we ask the question, can we apply the same type of spin to charge control protocols at the level of individual NVs? The answer is yes. And here is one first demonstration where we again reconstruct by looking at the target NV while exciting the source NVs, and we reconstruct then a magnetic resonance spectrum that agrees well with that expected from standard methods. Now I'm going to conclude with an anecdote, and this is to say that in preliminary conversations that we had internally in the group, there was, among my group members, there was a widespread skepticism that about these experiments. And there was a valid reason for that, because if we calculate the number of carriers that are being generated while exciting an individual NV, and we think of the chances of hitting with those carriers a defect that is a couple microns away, especially in the absence of an applied guiding electric field, well, chances seem pretty dim and translate into pretty unrealistic experimental times. So it was then very surprising for us to see that, and perhaps the reason why in practice we can actually see these processes taking place is because if we plot the inverse of the bleaching rate in here of the target NV, which amounts to, say, the unit time probability of ionizing the target NV, as a function of the power that we apply, we see a straight line. And this is actually surprising because I already said at the very beginning that these ionization processes and recombination processes are both two-step processes. And so the number of carriers that is being generated grows with the square of the power, meaning that then this probability of whole capture grows here with the square root of the number of carriers, not the number of carriers. And this is essentially telling us that the process is happening actually faster than one would classically anticipate. Now, I want to emphasize that there could be a number of reasons, and the comment that I'm going to make now, and with that I'm finished, has to be taken with a big grain of salt. But it was actually interesting to find out that there's a paper that came out recently that essentially models the diffusion of a carrier in a lattice with a defect, and essentially states that this process can be modeled or can be interpreted as a naturally occurring Grover search algorithm that essentially relies on the fact that carriers in solids move as a wave. And essentially it makes the point that the chances of having the carrier localized at the defect point grow with the square root of the number of sites that we have in that simulated lattice. And so I think it will be really fun to see what type of connections we can establish between our observations and this type of theoretical prediction. Well, with that, I'm going to skip the formal conclusions. I want simply to acknowledge the work in my group, and in particular, the work by Arthur, which was also seconded by Hattie and counted with the help of Damon and Aisha, and my collaborators at Sandia and elsewhere in Canberra. Of course, I have to thank the funding agencies, particularly NSF, for funding this project now over a couple of years, and you all for your patience. Thank you very much.